Our second focus today is on smart contract security. To discuss, please welcome to the stage Chain Security CTO and Blockchain PhD, and the first speaker of the day to be wearing shorts. Please give a warm welcome to Hubert Ritzdorf.
Thanks so much. Yeah, thanks so much for the kind introduction. Today I'll be speaking about the security of smart contracts. So I hope you have heard of smart contracts before. But in case you haven't, just imagine small programs running on the blockchain. We'll see a couple of examples later. And in particular, I'm going to talk about the security of smart contracts, but actually what we would like is correctness of smart contracts. So we will talk how maybe we could get to functional correctness of smart contracts. So initially, we're going to start out with this. So what do all of those have in common? We have an airplane, a Mars rover, a satellite, and a smart contract. Well, we don't want any of them to fail. We don't want our airplane to fail all of a sudden. And the same way, we don't want our smart contract to fail. Because traditional smart contracts cannot be upgraded, they cannot be replaced, and even if they can, by the time they have been upgraded, the damage is probably so big that, it might not even matter anymore that we have the ability to upgrade them. So they must not fail, all of these systems. However, what sets them apart is that while we have, for a while, been using very specific techniques to ensure proper functional correctness, called formal verification, for some of these systems, we haven't been doing so for smart contracts. For smart contracts, we still mostly rely on best effort services, basically meaning we'll have a look, we'll test around a little bit, and if it looks kind of okay, we'll go with it. So that's not really acceptable in the blockchain world of the future, where lots of funds are being handled this way, lots of important information is being stored this way. Imagine a real estate blockchain being hacked. All of a sudden, you're the owner of half of the country. That would be quite nice, but not really what we're looking for. So what we're going to talk about is how can we improve the situation, and to motivate that there's even a situation that needs improvement, we're going to look at some problems, some real-world problems that appeared. So this is a kind of paraphrased smart contract, an Ethereum smart contract, and you might be aware that there are these token smart contracts. You can buy these tokens, and the most important thing of a token is that the balances are being preserved correctly. So if I have 100 tokens, then I should always keep these 100 tokens, and the other way around also. You shouldn't just be able to create new tokens for yourself. So here, for example, we have such a token contract, and we have the typical transfer function, which allows me to send tokens to you. And in this transfer function, we have a check for sufficient funds. So we're checking that if I'm sending 10 tokens to you, I'm holding at least 10 tokens. So everything is well and nice here. And then what people did is they were a bit annoyed that I can only send funds to one person, so they introduced a new function. Yes, and also this is the state of the smart contract. Smart contracts always come with the code and the state. And as I said, they introduced a new function called batch transfer, which lets me send funds to multiple people at the same time. So let's say I want to send 100 tokens to everyone in the front row. Now I can do that in one transaction instead of in 10 transactions. So that is cheaper and faster. So I would prefer to use this batch transfer function. So this is all kind of a nice idea. And what does this batch transfer do? We see it calculates this total amount, which is basically if I'm sending 100 tokens to everyone in the front row, and there's 10 people in the front row, then the total amount is going to be something like 1,000. So the amount of checks the amount of tokens that I have to send, and then it's actually checking that I have this amount of tokens. So everything looks good. So let's see what the problem can be. So on the right side, we have seen the state. So I'm the sender of this transaction. You see my token amount currently is 20. Yeah, I'm not sure how well it's visible, but I'm going to start a new transaction where, in this case, in this example, I'm sending to 2 receivers, and I'm sending 130 tokens to each of them, which means that as the total amount, we're going to compute 130 times 2, and this all looks really good until the result turns out to be 4. So how in the world could the result turn out to be 4? Well, I don't want to go too much into details, but as you might be aware, computers have limited precision, so they store things with certain amount of precision. And here, if we use 8 bits for our variable total amount, the largest number it can store is 256. So we're trying to store 260. So what all it stores is the number 4. And then all of the other checks will pass. What the result is that after this whole transaction, I still have 16 tokens, but my 2 friends now have 130 tokens each. So I created tokens out of thin air, the one thing we really want to avoid. And this is a real-world example. So, and this is one of many, as you might have seen. And it doesn't stop, like, these are not just simple projects or something. In May of this year, a severe bug was found in one very popular and previously audited smart contract. So it affects all kinds of systems. So what we're trying to do is, as I said in the beginning, we're trying to provide formal guarantees for these contracts. The first step to that is that we mathematically model all possible behaviors of the smart contract and then try to prove that no bugs can occur. You can imagine it a little bit like a puzzle where there are certain ways you can go, and you're looking at all the ways and you're trying to see that none of them leads you to a bad state. But we'll see more examples later. So, and obviously this is really hard to do, so we will try to automate as much as we can and use state-of-the-art research to achieve all of this. And our system is called Verex, which aims to do exactly this, formal verification of custom functional specification of Ethereum smart contracts. So why is this even hard? Like, it's not so clear, like, why would this be a problem? So I will explain a little bit what the problems in this is. So this is a lot harder, for example, than just finding generic vulnerabilities. So last year here at the conference, I was talking about our system Securify that lets you find generic vulnerabilities. However, this is a lot harder. And why? I'm going to explain with a running example. So let's say we have a crowd sale, and this crowd sale is selling tokens and has a goal defined, a goal in terms of the investment it wants to reach. And we also have an escrow, and the escrow contract is going to hold the funds of the crowd sale, so the funds that were invested while the crowd sale is going on, and it's going to remember who paid in, so it's going to remember the deposits. And now we need some investor, so we have this guy here, Mr. V, who's going to invest 5 Ether here. So he pays 5 Ether into the crowd sale, and what the crowd sale now does is it remembers that some amount was paid in, so 5 was paid in, and then it actually forwards the funds to the escrow, who's going to hold the funds. And the escrow remembers that Mr. V now has 5 Ether. And the important thing here is after the crowd sale has ended, one of two things can happen. If we reach the goal, then Mr. V will get the tokens. And if we didn't reach the goal, then Mr. V can claim a refund. And but we want to make sure that, for example, none of the other combinations can happen. So in contracts, it will look something like this. We have the crowd sale, we have the escrow. And more formally, these requirements are that, for example, as I said, the escrow is going to remember all the deposits, and it's going to save the money. And it's going to allow you to do refunds maybe, but then it should also update all of these deposits properly. So at all times, basically, the escrow should have the money that it's pretending to have. So the sum of all the deposits should equal the escrow's balance. And also, as I said, investors can only get a refund, or in other words, cannot get a refund if the goal has been reached. So what we do is we formalize these properties. Informally, the sentence says sum of all deposits. We already saw this one, so we make a formal property out of this. As we see here. And then in the second step, we check this formal property. So here is the procedure that I already described a little bit before. So we have an initial state. The initial state is the state of the contract. So we saw in the example before, the state of the contract basically means what are all the variables and what are their values. So in the initial state, we can check this. And then starting from the initial state, there can be many, many different transactions. And these transactions, they lead to new states. So basically, we get this state tree. And now, from each of these new states, again, we can have many, many transactions. And it goes on and on and on. So now the problem in formal verification is that we have to figure out that none of these states, all of them that we see here, has a problem inside. So basically, we want to make sure that all of the reachable states are fine. So that for all of the reachable states, the conditions that we defined before, so for example, that the deposits equals the balance, holds. So that already gives you a feeling that this could be quite hard, because we'll get a whiff of this tree that is infeasible to brute force, and in general, we will also have an unbounded depth. So basically, we have an infinite tree, more or less. And if it's not infinite, then it's quasi-infinite in the sense that it's way too large for any computer to process. So far with our idea, I mean, we had the right idea. We wanted to check all the states, but we see it's not going to work the easy way. So that's what I meant with it's not so straightforward. So what we'll try to do instead is we will see what we can do. And to understand what this technique does is we will review the kind of alternatives. So the easy alternative is you do a manual review of the smart contract. And that's nice, but it's first of all time-consuming, and second of all, it's known to miss errors. The second option is called automated testing. So hopefully everyone does some testing for their smart contracts, but you can do further automated testing for your smart contracts. Such automated testing is called, for example, fuzzing. So what does fuzzing mean? So if we look back at our tree, what fuzzing does is it just generates a lot of inputs automatically and then executes the tests. And so, for example, it will generate a sequence of inputs that lead to these executions. So we'll get multiple executions. We can go very deep down this tree, but we're not going to cover the whole tree. And certain parts of the tree we are actually very unlikely to cover. And there's a number of tools out there that do this, and they can be very helpful because, as we can see, I mean, already we're doing something, right? We're covering some states, so we're doing progress here, but obviously we're not doing everything. So then there's another alternative that we can use, and that's called symbolic execution. So the idea with symbolic execution is basically that we don't execute the program normally, but all the inputs are symbolic inputs. So this might not tell you much, but imagine that normally if you call any kind of computer program or function, you have to give a concrete input. So you want to add two numbers, you say, I want to add numbers 2 and 4. But here you say, like, I want to add one symbolic number to one real number, and then it kind of tracks dependencies. And this allows us to explore states in a broader width. And however, because it has to track these dependencies, it's quite inefficient, which means that it becomes very hard, if not impossible, to reach further down this tree. Simply because there's so many states already on the second or third level of this tree that there's too many for us to execute them all. Again, for this, there's already a bunch of tools out there. Some of them already also open source that we have listed here. So now that we've seen the comparison, so what does formal verification can do for us? Well, as you can imagine, our goal is to check all these states. So, but how do we get there now? We saw that it's kind of hard to do. Well, with Varix, we'll try to do this. So how do we do this? Again, we have the smart contract, and we have this property that we want to check. We're transforming it into the formal property, and then we're putting it into Varix. And Varix will tell us either it's verified, or it may not hold in case it finds like one state where it doesn't hold. Whereas if it finds that with all states, so all parts of the tree, this is verified, then we know it will always hold. So, and what we tried to do with Varix is we tried to make the specifications as intuitive as possible. So they might not look intuitive to all of you, but the idea is that they are quite close to Solidity. So the smart contract programming language, so if you know how to program smart contracts, you can hopefully also specify these constraints. And they try to emulate what's most relevant. So for example, access control, so just as a reminder, access control is kind of the core problem in smart contracts because by default you have none. So everyone can interact with your contract, everyone can call each function, and you now want to build on top like who's supposed to be able to call which function. And so we can model access control, we can model state-based properties. So for example, things about time, like things, then we can model state machine properties. So you should only be able to go from one state to another, but not, for example, back. We can model something like aggregates, so we can express quite complicated specifications. And finally, something that Varix can do that other systems can't is it can argue across multiple contracts. So we already saw that in most systems we somehow have multiple contracts which are connected, and so we would like to somehow say something in this contract has to match something over here. That's what we can do with Varix. And all of this is built on linear temporal logic, which is a field that has been studied for a long, long time in computer science to kind of express precisely what we want and don't want. So now to the revelation. So how do we now deal with this mega tree? So instead of instead of like building up this giant tree, we'll try to build a smaller tree. So why can we build a smaller tree? So first of all, again, we'll use symbolic execution to build parts of the tree. And already with symbolic execution, we can reduce the size of the tree because we don't have one state for each concrete execution, but we have one basically per function, more or less. And that already reduces the width. And now we will use program abstraction to bound the depth. So basically what we will try to do is we will try to think about these properties, and we will abstract away as much as we can about the program. So just remember in the beginning, I showed you a state. It had many variables, but many of those we actually don't care about for specific properties. So we will only remember those that we care about. The rest we abstract away. That's why we can reduce a lot of what we care about. This is, as you might expect, quite hard to do, because I just said we abstract away, we ignore certain parts and so on. This can get very tricky. So this part is still ongoing research to make sure that all of these things hold correctly. Some more exotic contracts are very hard to verify because they have very specific properties. So this actually works. So we can certify certain properties. We did a test set of over 100 contracts with over 100 properties, and it takes roughly 1 minute to certify such a property. And another benefit that you have is we see a lot of customers that have, like, they write a smart contract, and then a year later they bring out a new version of that smart contract. And if you already have the properties and you already decided what the system should do, then you can reuse most of these properties because most of them should probably still hold on the new system. So the reuse is actually quite powerful. If you want to see the demo, you can go to varix.ch, and for more information, you'll also find there and on our website also. So as I said already, this is actually tricky research. So this research has mostly been conducted by the ICE Center at ETH Zurich, where chain security is one of the associated startups. And so to summarize, what do we have? We have what we want to achieve is the safety and certification for smart contracts. We want to make sure they do not fail. For that, we built Varix, so a system where we have smart contracts, we have properties, and we can decide are they going to be verified or not. For Varix in general, it's of course different than, for example, Securify, which I presented last year, because clearly we need some kind of expertise to use it. We need to be able to write these properties. So it's something that we're currently exploring how to best use this. But it seems that it needs some expert interaction. We compared Varix to other techniques in this pyramid, where basically we said that with fuzzing we can cover some very deep states, but there's only going to be some states. And with symbolic execution, we can cover a lot of states, but only on a very high level. And with our technique of symbolic reasoning plus predicate abstraction, we can reduce the size of this tree so we can actually check the properties that matter. So quick information at the end. So this is about chain security. So we are, with tools like this, we are doing smart contract audits for all kinds of systems. So mostly Ethereum, but also, for example, Silica, Hyperledger, and so on, EOS, and we're also reviewing low-level blockchain implementations and protocols. So, for example, proof-of-stake implementations, and provide general consultation about blockchain security. And we also started a monthly Ethereum Security Digest, which not sure if the QR code works, but if it works, I mean, if the resolution is good enough, but if it works, then you can register there. Otherwise, just go to our website and you'll find the link there, chainsecurity.com. Thank you very much.